Okay. So first of all, I would like to thank everyone for taking the time to be at Defense for presentation for my PhD thesis, which is titled General Level Generation. It doesn't. Oh, okay. So first, I want to thank the committee members, starting with my supervisor, Julian Tigilius, Andy Neelan, Diego Perez, Michael Cook, and Santiago Antonian. So just to start really directly what I want to do. So what I try to do is I want to find AI techniques that can generate levels for more than one video game. And this technique doesn't need a lot of change when you try to apply them to different video games. So just to understand it more, let's do a little bit of flashback and go a little bit backward. So what is a level? Just so everyone, like people who doesn't know what does this word mean, a level is like a space where players can interact with the game itself. Also, you can see it as a medium where game designers and developers guide the player for certain experiences. Examples are the first level from Super Mario Bros. And the dungeons in The Legend of Zelda. You can consider them as a level. I also say level generation for people who doesn't know. Level generation is using an algorithm to generate levels for a specific video game or for a video game in general. It's something that started like early in 1980s for games such as Rogue, Elite, and Beneath the Apple Manor. So usually designers like to use them because they enable new types of games that you get new scenarios every single time. It enable like people to not only memorize the levels they have, but every single time they get new levels, so they need to adapt to what's happening. Also, some other people might use it to tailor the experience where the player is playing the game. So for example, if you're playing a level and then I have my algorithm might be recording what I like or enjoy in the game, and then it could generate level that have more of the stuff that I'm like enjoying. Another thing, some people use it even like in debugging and at the beginning of the game just to understand how the games and the rules are interacting with each other. And then maybe they could fix the game rules and stuff like that. The problem usually when you look at level generation at its current state, especially when I started my PhD, most of like the level generations that's used in industrial games and games use heuristics and rules. They are like, oh, here's a couple of rules, follow them, and if you follow these rules, you will get a game. For example, in Spunk, a very famous indie game that use precision content generation or level generation, what it do is it stitch these hand author content beside each other in a way that you have a path from a starting location in the top of the map to the bottom of the map. If you try to use that algorithm for anything else, it will not work unless the premise of the other game is similar to Splunky. You need also to traverse from the bottom to the top, and these hand author content is designed for that. And when you look more, people always look at level generation as this optimization problem. And the reason is because levels are functional content. You can't have a level that doesn't work. Like, for example, a game like Super Mario Bros. If you have a big gap and you can't jump that gap through, then the level is broken. And people won't say, oh, everything in the level is good except that one gap. They will just say that's a broken game because of that level. So we always need to have this functionality constraint or a certain quality to be passed, at least to have the content itself. So that's why most of the people look at levels as optimization problem. But at the same time, this is not 100% true because levels are also subjective. Like if I say this, I like this level and then showed it to Julian, Julian might say it's not that good, and he might do another level and say this is better, which I might not agree with him. And the same with maybe Andy or any other person. Every person has their own preference and it's a little bit subjective. So just optimizing for a certain criteria might not be the best idea. So what I propose is to find these techniques and metrics and methods that can generate levels that are still playable, because this is the main thing, because the levels are functional, and at the same time, they are diverse. I don't want to have one single level. I want to support like getting a lot of different levels, so it can fit the different tastes of like users or designers, and they can see what exactly they need to do now. But at the same time, the most important thing is I want it also to be easy to be moved from one game to another with minimum amount of change. I don't want every single time you create a new game, let's think about what should we do. I want them, okay, here is, I will plug this algorithm and then I modify and tune it a little bit, and ta-da, you have a result. This leads to the thesis statement, which says we can computationally generate a set of diverse levels for any video game through searching either the level space or the generator space. The most important thing in that statement is these three highlighted words, which is the level space and the generator space and diverse. So we want not only finding levels that are diverse, we also want to search also for level generators that can provide also diverse level. It's just like a little bit a step ahead, but we're gonna go in everything in detail. So from that statement, I could just specify a group of goals that I try to achieve, which is divided into two parts. The first part is searching for the level space itself, and the second is searching the generator space. So, and what I always need to find in each one is general techniques to be used, general quality metrics that I can say, yeah, can work. And maybe general diversity metrics, which can work between different games, and also apply it on multiple different games. The first part is searching the level space. So searching the level space is looking for techniques and metrics and methods to generate levels that are playable and diverse. So we just want to do that and make sure that we can apply them to multiple different games. So it's easy to transfer it between games, just as a proof of concept. So when I started my PhD, I had that idea about general level generation, and I asked Julian, what should I do? So Julian just told me, why not look in general video game framework? And I was like, it has the word general in it, so it might help me to solve the problem. So I started looking into that framework, and as you can see, that framework is an AI framework that provides multiple different types of games and also provide a lot of different AI algorithms that can play some of these games in kind of interesting, like kind of good, not amazing, but kind of good. For example, these are three different games from the framework, which we use in that first work. The first one is called Zelda, where you control that hero and try to get like a key and then go to the door and avoid being killed by enemies. The second one is called Snowman, where you try to build a snowman by putting the pieces on top of each other until you make a snowman. And the last one is called Freeway. And Freeway is as simple as crossing the streets in Egypt. You just try to cross without getting hit by cars. So I started looking in the framework, and as you can see, when I started, there was no way you can inject like level generation in the loop itself. So I started designing this interface that helped me to do that. And the interface is as simple as it needs to provide the level generator with something called the game description object. So the game description object is that object that have all the information about the game, such as what is the like sprites or objects that could be in the game, what are their properties, are they controlled by the player, are they harmful to the player, stuff like that, and the interactions between them, and also provide a forward model. So the forward model is just to help us to simulate the game. Like I could just, here is a level, and tell it, can you tell me if it's playable or not? And it uses an AI agent and return if it's playable or not. And in return, the level generator has to return just a generated level for the framework back. So I started designing the first algorithm. So I was looking in like a couple of like old research, and I found that search-based approaches are very common to be used, which use usually an optimization algorithm. So I decided to use an algorithm called feasible and feasible to population, which is just an optimization algorithm that try not only to optimize certain quality, but also satisfy a group of constraints. And then I designed these general constraints that make like the level more accessible, and also doesn't make us do a lot of simulation, just eliminate some of like the broken levels, for example. So it removes any levels that doesn't have a player, because you can't play the level if you don't have a player. Also, it removes all the levels that have like the player can die in the first like few frames, because they are not accessible for humans. If you can die in the first 1 or 2 frames, that's not accessible. And for our fitness, it was just something simple, which is like, is the level playable or not? And if it's playable, how long does it take to finish the level? Because we didn't also want to generate very easy levels. So we compared that like generation algorithm to 2 other algorithms we decided to design. One is called random and the other is called constructive. Random is just like get the objects and just place them randomly in the map, while the constructive, it tried to place them in a certain way that it looked nice. And we tested them on the 3 games I talked about, and then asked people to rate them and see which one is the best. We can see that the search-based approach have like a lot preference than all the other 2 techniques, which what we wanted. But at the same time, the random was better than the constructive. And when we look a little bit in detail how they are, why people prefer random or constructive, is the reason is constructive never cared about making a playable level, but only nice looking levels, while random was slapping random objects. So there is a higher chance when you slam random objects that you have every single entity in the game and became still playable. Like for example, in these 2 pictures, the random have a key and a door, so you can win the level, while the constructive, even if it look a lot better, you still don't have the key. Okay, looking back at our goals, so now we have a general technique to generate, which is a search-based approach using that optimization algorithm. We define some general quality with some constraints in it, and also we apply them to 3 different games. So we apply them multiple games. But as you can see, we never address diversity. And there is nothing that can tell us if we ran the algorithm multiple times, the output will be diverse enough between each other. And usually these algorithms take a long time. So it's kind of like a waste of time to take very long time and in the end find slightly different levels. So I started looking around, and there was this new algorithm called Map Elites that was just starting to happen. And for people who doesn't know Map Elites, so Map Elites is a quality diversity algorithm. So what it tries to do is it tries to enhance the quality of the level itself, but at the same time, it tried to make sure that the levels are also diverse explicitly. For example, what it do is like it have like something we call behavioral characteristic, and it divides the search space of the levels using the behavior characteristic. For example, let's say the behavior characteristic is number of enemies. And whenever it finds a new level, it calculates that characteristic, which is the number of enemies. And in that case, we have 3 enemies, so it's gonna be inserted in 3. And then it finds a new level, and that new level is having 1 enemy, so it gets placed in 1. But if it finds another level that have the same value as something before, it compares these 2 assets with respect to each other and picks the best. But since I talked that we wanted like some constraints just to eliminate a lot of this computation power, so I wanted to modify that Map Elite algorithm so it also have constraints. So I designed a new algorithm called Constraint Map Elites. And Constraint Map Elites is just a combination of the FI2 pop algorithm with the Map Elites algorithm. So the whole idea is each cell, instead of having 1 level, it have a group of levels, and some of these levels are trying to satisfy the constraints, while the others are trying to improve the certain quality I'm trying to do. So since we are also doing general level generation, so I decided to try a new game. And the game I decided to do is a genre called Bullet Hell. For people who doesn't know what the bullet hell games are, so bullet hells are these types of games where there is too many bullets on the screen and you need to evade them, but at the same time try to kill the boss that like attacking you with these bullets. There is a lot, it's very famous. There is a lot of like famous games. This is a video from a game called Toho, which is one of the most famous like bullet hell games out there. So we wanted a way also to describe how these levels look like. So I designed like a scripting language. It's called Talakat, which means bullets in Arabic. And that scripting language is simple, that it consists of two parts. The first part is called the spawners, which is it defines how these bullets are interacting and moving in the space. And the second one is called the boss section, and it only identify how the boss is using these spawners over the course of the level. Does it spawn it when it's going to spawn it, where it's going to spawn it, and if it needs to delete any of the old spawners. So I use that constraint map elite algorithm, and we made the constraint on minimum number of bullets and maximum number of bullets. Something just to make sure, because you don't want a bullet hell level that doesn't have any bullets. And at the same time, you don't want a bullet hell level that have too much bullets that you can't even live in the game. And also, like, by removing these like parts, it make it faster for computation. And our quality that we were trying to address was just like win the level, just how far you are to win the level. But that's not enough. We say that constraint map elites need something to calculate the diversity. So we designed these three different human behavior characteristics. The first one, we call it the entropy. So entropy means how much is your agent is moving. So if your agent is moving too much, it will have a high entropy. And if it's not moving a lot, it will have low entropy. The second one, we call it distribution. And distribution is just a measure of how much of the screen is covered with bullets. So if there is a lot of bullets covering the screen, you will have high distribution. And if you have a small amount of bullets covering the screen, then you have low distribution. Lastly, something we call risk. And risk means how much bullets are surrounding the agent at any point in time. So, and if there is a lot of bullets around the agent, then this agent is playing very risky. And if there is not, the agent can just chill down and do nothing because it's not a risky play. So we ran this algorithm for 180 generations. And as you can see, it's kind of like found up to like almost like 140 levels, which is kind of like 15% of the full map was covered, but it was still increasing. So if we run it for longer, we will get more coverage. We are sure about that. So we decided to look a little bit deeper into how these levels look like. So just we picked two of the dimensions because it's harder to like show 3D like dimensions. So we picked only entropy and distribution. And as you can see, levels with low entropy, basically the AI agent is barely moving in the level. It's like most of the time it's just staying still or moving a tiny bit. While when you have high entropy, it's moving everywhere. And if you have low density, you can see that the screen is covered with bullets, but not too much. But if you have a high density, almost the whole screen have bullets. And the reason for that, it doesn't mean to have more bullets. It's more about like, oh, you want high density, so the algorithm decided to make bigger bullets, so because bigger bullets can cover more of the space itself. And also looking at all these four, you can notice that they are kind of totally different in the way it plays, even the way it looks like and everything. So looking back at our goals, now we have a new technique, which is the constraint map elites, which is better than the previous one, and we can use it. And we introduced diversity also, but we didn't introduce general diversity. We have to define this diversity metric. We have to define what's entropy and what's distribution and risk, which cannot be transferred easily to any other type of game. So we need to address that problem if we want to move forward. So as usual, I decided to change the framework to a new game, which is Super Mario Bros. For people who doesn't know, it's a very famous game by Nintendo, where you try to avoid enemies or kill them until you reach the goal, which is to survive. People were saying that I did that just so because I need a Mario level in my research or I'm not going to be graduating. But that was not the real reason, of course. I just wanted to use that framework because there is too many research happening in that area that could help influence how we could do that general diversity metric. And also there is like a very good A-star agent that can play the game, which you can see down there. It plays almost perfectly the game while avoiding every single enemy and everything that's on the way. Also, instead of generating a full level, we just decided to generate a small subset of the level, which we're gonna call it a scene. And the reason for that, we just didn't want to do too many computation for a full level. And we just said, if we can generate a small scene, that's pretty good. Then we can later stitch this scene together with another algorithm to have a full level. So I start looking around what could be a general behavior characteristic. And when I look at a lot of different designers and read a couple of books about level design, a lot of people design their levels around certain game mechanics. So if your mechanic have killing enemies, then it try to design levels around doing that action. So I was like, okay, game mechanics are pretty general term. When I tell someone what's your game mechanics, he can identify them directly. So it might be a good idea to use it as a behavior characteristic. And for people who doesn't know what the game mechanic is, it's anything that happens in the game that will change its state. For example, in Mario, you could jump on top of like a pipe. You could jump on top of Goombas to stomp them to death. You could just push a Koopa shell to kill another enemy. You can collect coins. There's a lot of them. And these are some of the ones we use anyway. So since our level now is short, we decided just to make the constraint directly to be playability. We just want a playable level or a playable scene. But for our fitness, we decided to make something that makes the levels look nicer and easier to read. We didn't want to have a lot of noise and clusters that's not being used, just want a clean look level. So we did the simplicity fitness that always try to minimize the clutter on the screen and also tries to cluster similar objects together. For example, if you have the same amount of objects, it will make them all close to each other and just separate them away. So we ran that algorithm for 1,000 generation, and in 1,000 generation, we could find up to 40% coverage, which is pretty good because like you can't reach exactly 100% coverage in that problem because some of these mechanics don't happen by itself. For example, you can't kill an enemy without jumping on top of them. So you can't have a kill enemy and not jumping. So we decided to start looking also on how these levels look like. And these are just two of the dimensions we're having. One of them is the stomp kill, which you jump on enemy to kill. Another one is collecting a coin. And our dimensions are just pretty basic. If this mechanic happened, then it's happened. If not, it didn't happen. And if you look at this level, it's interesting how it evolved this level such that it put the enemies on this and the coin on the path of the algorithm, because the A-star algorithm that plays pretty well doesn't care about anything except just winning the level. It doesn't care about killing enemies. It doesn't care about collecting coins. So if you didn't put it on its path, it will avoid them and it will never happen. So that's why you can notice for the stomp kill, there is always a gap before the enemy, and the enemy is kind of stuck on a smaller place. So the gap will force the agent to jump, and when he jump, he will usually land on the enemy because it's on a small space. And for the coin, it decided to put the coin on the pass at the beginning of the level because it guarantees that the agent will not be jumping or doing anything, so it will take it while it's running. This is kind of interesting because, as you can see now, we have levels that have all the combination. We have levels that doesn't have any coin or no monster killing. We can have like killing the Koopa or collecting a coin or both happening together. So let's look back at our goals. Now we introduced some new general quality metrics, which produce these nice looking clean levels. And we also introduced general diversity that could work also between different games, but we still didn't now try these on multiple games. So that was just an easy thing. So we decided that why not just plug everything we learned in the general video game framework. And so people might say, where is the mechanics coming from? It will come from the game description object that the general video game framework is providing. And we use the same constraints as before, which is we want to have playable level, and we use the simplicity as a fitness function. So we tested it on 4 different games. The first game is Zelda, which we just talked about. And the second one is called Solar Fox. And Solar Fox, you control that spaceship that's trying to collect all these diamonds in time before it dies or hitting anything. And there's a game called Plants where you try to, it's inspired by Plants vs. Zombies, if someone knows about this game. And you try to build these plants on the left side of the screen to avoid zombies coming from the right side to kill you. And the last one is called Portals, where you use these portals so you can traverse the game space easily. And it's inspired by the game called Portals by Valve. And the most important thing you notice is Portals have the highest number of mechanics, followed by Solar Fox, then Zelda and Plants. So when we ran our algorithm, we can find that Zelda and Solar Fox will only be able to get like around 10% coverage, which kind of okay. It's not the best we can find, but maybe some of these mechanics can't happen and also win. Like for example, some of the extracting mechanic is the player dies. You can't win a level and die at the same time. It contradicts. And on the other hand, for Solar Fox and Real Portals, they have very small coverage, less than 1%. And we think the reason for that is curse of dimensionality. Everything went to hell because we have a lot of dimensions. And it couldn't cover too much, it just covered a very small space, which is something we need when you're trying to use these techniques, you need just to keep in mind not to have too many dimensions. So we also started to dive into how these levels look like. And these are the sample level from each of the generators. So for Zelda, as you can see, it's pretty clean level. You have a key and a door and a couple of enemies, but there is an extra key. And we think if you run it for a little bit few more generations, the Simplicity Fitness will probably be able to remove that extra keys there. On the other hand, Solar Fox became too simple that it became not very interesting anymore because Solar Fox is heavily designed on having a lot of different objects that you are trying to collect. For Plants and Portals, they became also simple levels, but for Portals, it ignores the main mechanic. You can walk now directly to the door. There is no water preventing you. You don't need to even use your portals to traverse the level. It became too simple. And for Plants, it's also the same, where you just need to plant one plant in front of the zombie, and then you win the level. But the main problem for these to be like that is we think that the AI algorithms that play Portals and Plants didn't do well, because if you look in the GVGI framework, the best agents that play these games barely win them. So I think the evolution tried to adapt to find playable level that these agents can play, which just ended up having these simple structured levels. Okay, now we even applied on multiple games and we have kind of okay results. So we could now start on the second part, but before doing that, there is one problem I never addressed, and I'm the one who introduced it, which is the small level, which is scenes. So I wanted to try to find a solution before I finish my PhD to that problem. So we introduced that idea, which we call stitching scenes. So the whole idea is to try to stitch these small scenes together in a certain way, according to certain criteria, to generate a bigger level. So, and we decided the criteria is called mechanical similarity. So mechanical similarity is just trying to compare the mechanics of a certain level by the generated level. For example, we want to generate a new level that plays in the same manner to one of the original levels. So what we do is we make the A-star agent play both levels, and then we record what mechanics happen in each playthrough, and then we try to compare them using a string comparison or whatever, and then identify what is the mechanics that it missed and didn't do, and what other mechanics that were extra and need to be removed. And our optimization algorithm can just work on minimizing this stuff. So we use the FI2 pop algorithm that we talked about before, and we made the constraint is to be playable. Even we know that each scene is playable, we can't guarantee if you slap stuff together, it will generate a bigger level and still playable. So we just say, why not just add the playability as a constraint? and our fitness function is how close we are similar to the original level. We tested that on 3 levels from Mario, which is level 1.1, level 4.2, and level 6.1. And this is a histogram of the playing these levels with the A-star algorithm. And as you can see, the A-star algorithm avoid killing enemies and also hitting blocks and other stuff, because it's not what it tries to do. It just tries to win the level, and it do a lot of jumps. This probably will hurt the generation, because if you don't need to kill enemies, there is no need to have enemies in the level. So when we ran everything, we looked at the match percentage of the generated level, and we can see that we get kind of decent match percentage, almost 80%, and the number of extras decrease over time to be around 20%, which is okay, because it might not be able to reach 100%, because maybe the scenes we are using to combine them together, maybe they are not having every single thing we want to do that play trace we want. So looking at the playability of these metrics, we also compare them to 2 other algorithms. The first one is random, which is just slap random pieces, scenes after each other and get a level. And the other one is a greedy algorithm, where it put a scene and then it picks the next scene and the next scene, such that it increases the match percentage. And as we can see, that only the evolution was able to find almost 100% playable levels, while the other suck at finding playable levels. But at the same time, we also measured how diverse the generated levels over different runs. And we find that our also evolution algorithm, the levels generated are not very diverse enough between each others. So we decided to look at these generated levels and the original levels. If you look at the original levels, they kind of look very diverse. You have tubes, you jump over them, you have groups of enemies, you have these blocks and interesting structures. On the other hand, our evolved one looked pretty weird, going up and down, having a lot of gaps in it, having these long, tall walls, enemies in certain weird places, never grouped together. And we think this is due to multiple different reasons. One of the main reasons is our A-star algorithm never cared about killing enemies or anything, or never cared about what it's doing other than jumping. So if you jump on top of a tube, it's the same to jump on top of an enemy. It's the same as jump on top of a couple of brick blocks. So that's why there is not a lot of tubes appearing, because it doesn't matter. So that's one of the things. Another reason is our simplicity function that we were using to evolve these scenes might also make the scenes more flat and more too simple, and doesn't have all this big, interesting structure in them. So we might need to improve on these parts, but so far we think that our algorithm performed pretty well. So still looking back at our goals, now we have a new technique for stitching the levels together, and we have a new general quality metric that we can use to stitch the stuff. So at that point, I decided this is enough for that part of my thesis, and let's start researching a different thing. So the second part is searching for the generator space itself. So to remind you, what we need to do is, instead of finding levels, we are trying to find level generators that can produce the levels that we want. So it's kind of like searching the meta space of levels for something that produce what we want. So when we looked in the research, there was not a lot of research that had been done in that area. And usually it's because it's a very hard problem. How do you define a level generator? What is the way to do that? There is a lot of different ways you can think about it. You can think about it as a neural network. You can think about it as a description language, similar to Talakat. You can think about it as probability distributions and so on. But I can't go all over them and try each one. So we just decided to pick the top 2, which is the neural network and description language. And it's because they have different ways of interacting and finding content. That's the main reason. So for the neural network, for people who doesn't know, a neural network is a great function approximator. It can approximate any function. So by this, it can approximate a level generator, because if you look at level generation as a function, then it should be able to do that. And the reason for picking it is because there is a lot of research in neural networks and they have impressive results. And every cool person is using it these days, and I wanted to join the cool group by doing that. So because it's a harder problem, we picked a smaller, simpler problems to try to solve. The first one is what we call the binary game, where you try to make sure that everything in the map is connected and there is a very long path in it. And the second one is called Zelda, which is the same as Zelda before, where you try to make sure that the level is playable by having a key and a door, and there's no enemies close by you, and you can reach this key and door. And the last one is a Japanese puzzle game called Sokopan. And this game is like you have a player and you try to push crates on the or boxes on top of these like target locations. And the main criteria is you need to have a player and you need to have number of boxes equal number of targets, because if it's not, you can't win the level. So the first thing is how we're gonna train that neural network so it can be a level generator. So if you have a huge amount of data, that might not be a very hard problem because there's a lot of techniques. Supervised, self-supervised, and supervised can do any of these. But the problem is it's very rare you can find a huge amount of levels that with a high quality. And even if you find them, they are for particular certain games. So you can only generate for that game. So another way you can train these networks is to use a reward function using reinforcement learning. So reward function is just a function that will tell you if you did an action or you generate a level, it should tell you if this action or level you did is good or bad, and give you like a positive reward or a negative reward. For example, so imagine this is a state, like a level, and it's kind of broken. As you can see, it's a Sokopan level with no player, and it's missing also additional box. So the system will ask our neural network, what do you want to do? And the neural network will reply with an action. For example, in here, just place a player in that location. And because of that action, the system will see, oh, that was a good action. Here is a reward, a positive reward. But for example, if the neural network action was to remove the box, then the system is saying, oh, that was bad. Here is a negative reward. So before we start training, how do we look at these states and actions, just for people to know? So we have multiple different representations for that. The first one, which is the easy one, called the wide representation, which you get the whole state of the level, which is how does the level look like right now. And then the neural network has to respond with an action. The actions consist of a location and a value. So I tell you, at this X and Y location, I want to have an empty tile. The next one was like, oh, this you want to give the network to give a location and an action. That might be a little bit hard. So why not try to make it simpler problem by instead of like giving it a level and ask it where to modify and what to modify, maybe we could give it a level and a location and then ask the network only, if you have that location, what do you want to do? Do you want to change it? Do you don't want to change it? And if you want to change it, what is the value to change? For example, in here, it's changed it by adding some tile, like solid tile. The third one is something hybrid between both of them. We still want to make it more controlled to be easier for the networks, but at the same time, we want to give the network a little bit flexibility. So the input space is the same. So it's a map and a location. And then we ask the network, what do you want to do? The network could just modify that location, or it could say that location is not good. Maybe let's go up because there is more interesting stuff up to modify. Then we started training the network, but we had a question to do that. How much the agent should modify from the map? Should modify everything on the map, give it this power to do that? And that was our first intuition. And we did like a small experiment doing that on the binary game. And as you can see, it was pretty perfect. It finds the best level ever, which is this zigzag level in binary, which means everything is totally connected and the path length is very long. You can't find anything longer than that. But the problem is when you reuse this network over and over and over, it only generates that level, or maybe like rotate it a little bit, but it's the same level. So the network didn't become a level generator. It just found a good level and just became that one level. So it didn't work. Giving a full change for the map will always ended up to override everything to get the best. So we modified that idea to only give it a change percentage. So it can't change more than a certain percentage. And by doing that, the network starts to try to find what is the best action it should do in this amount of small changes so it can perform well. And as you can see, if I give it that input now, it responds with a level. And if you give it a different input, you will get a different level. So we start training now our algorithm using our neural network using an algorithm called proximal policy optimization. We did this on the 3 games, the binary, Zelda, and Sokoban. And we did them using 3 representation, which is narrow, and turtle, and white. And we fixed during training the change percent to be 20% because we found that's a good value, so it doesn't do too much changes in the map. So looking at the results, you can see that for the binary and the Zelda game, that's during inference. We just like, after the network is trained, we run them multiple times and just collect how many of the level generated is successful. So for binary and Zelda, we're almost at 100% success rate. But for Sokoban, we had only 25% success rate, which was pretty low. So we start looking at the level generated, and we find that 86 of the generated levels are playable. But our success rate was defined not only just playable, it has to be playable and have more than 20 steps. But most of the level generated was less than 20 steps. So we think it's just because it's a harder problem, it might need a little bit more training just to find a better strategy to increase the success rate. So looking now in the generated content, and as you can see, like each one is behaving differently in the way it's like modifying the space. For example, the Y representation is already done, finishing, because it always does a minimum amount of change in the map because it has access directly to every X and Y position, so it can just directly change what it needs to change. On the other hand, the turtle, it's moving around and it tried to move in these passes where it could do the most amount of change in them. So it make intelligent movement around. And because of that, it give a different style for this generated map. On the other hand, narrow doesn't have any lot of control. So it usually just like wait until it finds interesting locations. Just like, oh, let's modify that location. So overall, they have similar success rate, but they have different styles because the way they are addressing each certain location and modifying them, which is a good thing because now you could use them for like generating different styles. So looking back at our goals, right now we introduce a new technique to generate to find generators, and we apply it to multiple games. The quality metrics were not general. There was a couple of quality metrics, but they were game dependent. So we didn't solve that. And at the same time, the diversity was kind of like implicit and not explicit with using the change percentage. So we can't guarantee that the generated stuff are 100% different, but we know they are different, but they might not look different. But I think that's fine because it's a hard problem. So at least if we can solve a little bit of it, that is a good contribution to it. So the second part and the last one will be just instead of using the neural network, we use a description language. So I designed the language, I call it marahil, which means levels in Arabic. And this language can define like a level generator easily by just putting these pieces together. It consists of these 5 sections, which have all the information about how it should, like what is the tiles it should be in the level, how these tiles have relation to each other. If I want to divide the map into several regions and then do them. And then the last part is called the explorers. And explorers are the most important part of the whole system because they define how exactly you're gonna generate the level. For example, that explorer, it starts saying, oh, fill the whole map with solid. The next one tell you for every region you have, empty the center of it and make it empty. And then the last one, it tell it to connect everything in the map so there is no isolated areas. So we decided to evolve only the explorers and not the whole script because they are the core of the generation. So it makes the problem easier. And we used for that a multi-objective optimization algorithm called NSGA2. So this algorithm, what it do is, if you have more than one fitness function or a quality, it tried to optimize in all these qualities at the same time and try to find all the good solution it can find in that space. For example, binary, we have two fitnesses. The first one is a number of regions. We want everything to be connected, so we want the number of regions to be kind of one. And longest, shortest path, which we want to increase the shortest path in the level. Also, as you can see, the explorers need to modify something. So we decided to initialize the map also randomly at the beginning, and we apply them to the same three games that the neural network worked on. So for the binary, that's what's called the Pareto front, or as sometimes I call it the burrito front, where this front, it shows you every single level generator it found that is good. And as you can see, we never found a generator that can get 1 and 1 on both axes, because the value 1 means it's 100% it can do that, and 0 means it can do that like fitness by 0%. And we didn't find like something that can solve the problem, but we find a couple of interesting ones. So we just picked that one to look more in details for it. If you look at the generated levels, they all have these loops in them. They look like very loopy, but usually the loop is not fully connected, which is pretty interesting, because if you did a loop, you usually end up by having very long paths. And I think that's the reason why it's have long passes in it. And sometimes, occasionally, it have these like small one tiles that's not connected, which could be easily solved later. But the good thing about using this method is we can dive into the code itself and try to understand how this generator is doing its stuff. For example, that generator, what it do is when it gets a random noise at the beginning, it tries to connect all this noise using these like short lines, vertical lines, and try to connect everything using them. And after it does that, it tries to find any big open space, and then it puts some solid tiles in these big open spaces. For the other two games, Zelda and Sokopan, they had more dimensions. For example, Zelda had 6 different dimensions, 6 different fitness function, and Sokopan have 4. And usually multi-objective optimization don't work very well more than 3, but we decided to go with it anyway. So if you look at just these two graphs, you will find that the y-axis is the solution length. So only in Zelda, you can only find up to 14%, which kind of means you only have 14% playable levels you can generate. And for Sokopan, you have less than 6%. So we look at the generated levels. Sorry that they look ugly and not like with tiles, they're just colors. But just for reference, green is the player in both games, and red and blue in Sokopan are crates and tiles, while red in Zelda is enemies, and the other two colors, which is yellow and cyan, are just the key in the door. If you look at all the levels, barely we can find something playable, and some of them might look playable. For example, the first level, the top left of Sokopan, you have 1 player and 1 crate and 1 target, but at the same time, that's not playable because you cannot push that crate to the target because it's trapped. So because of that, we started to dive into the code for these things, but they were pretty not intelligent, their code. So what they were doing is, after you get the noise, they try to erase some stuff from that noise intelligently, like we're using some like random functions. So it tried to erase some of this stuff, and then you end up by the level. The thing is, sometimes you start a level, since noise, you might not have a player, you might not have crate or target. And so you're never gonna fix that by adding them, you're always gonna erase. So that's why you have a huge non-playable levels. Okay, looking back at our goals, we introduce a different technique now for searching for the generator space. We didn't have general quality, we have just quality, similar to the one for the neural network, and we applied on still multiple different games. I think I've been ranting enough, so let's just wrap it right now. So looking back at the thesis statement, it says we can computationally generate a set of diverse levels for any video game through searching either the level space and generator space. I think we did a good job in doing that. Looking back at the goals, again, For searching the level space, we found like new algorithms that can be used to generate levels. We can find another algorithm that can be used to stitch the level to be bigger levels. We propose general quality metrics and general diversity metrics that can be used on multiple different games, and we even test them on a lot of different games. So for that part, first part, we think we are okay with that, and there might be a little bit of like some games didn't work well, but this could be left for future work. On the other hand, for searching generated space, it was a lot harder problem. So let's not be hard on the results itself. So we found like a couple of techniques that were able to generate the content, and it could be used anywhere. We applied on multiple games. We have a couple of quality metrics and like implicit diversity metrics, but we might need more like work in that area just to find better ways of representation to solve that problem. So that's why the future work for the level space care usually about fixing like these small problems or using it for more different applications, such as like try to find a better fitness functions than our simplicity. Maybe get some fitness functions from photography or anything from photography about composition or from painting, and try to make a function out of that. Also, we could use the generated like scenes and levels to create tutorials for AI or humans, because since we can generate levels that doesn't have any mechanics and then generate a level with one mechanic, then can generate another level with another different mechanic and then combine them later. That kind of like a building this curriculum, like, oh, let's play each of these mechanic in isolation and then combine them later, which is pretty interesting. And Mike Green is working on that in his PhD. And the last thing we right now, all the mechanics we are doing were automatically were hand designed. So it would be good if we can get from other fields such as event detections in soccer matches and stuff like that, ways to detect the mechanics also dynamically, which we're also working on with Mike Green for his thesis. For searching the generated space, there is a lot more need to be done. We could explore different representations. We only explored two of them. What about the rest? Maybe there is some interesting representations that will be better than these two. We might want to explore using general quality and diversity metrics, similar to the ones we proposed from the previous work. We could explore different ways to train the neural network, like maybe cooperative, you have more than one agent and each one trying to help each other to build the level, such as like similar to the cooperation between humans when trying to build a level. We could also explore better ways to find the Marahil levels and Marahil generators. This could be done by using a different algorithm. It could be by, instead of initializing by total random noise, we could just initialize by total solid or total empty and ask it to modify that. So there is a lot of like different avenues and ways we can do that. And by this, I would like to thank everyone, and that's the end of the presentation.
Thank you very much, Ahmed.
You're welcome.
Great.
I hope I didn't take too much time.
Well, do you want an answer to that?
I'm sorry.
No, so we went a bit over time,
yeah.
and we do have some time limits to sort of adhere to. So without further ado, I think we should take questions from the audience with a view to moving into the private question session with the committee in 10 to 15 minutes. Okay. So let's start with people who are not, people who are not in the committee. And I have actually never managed 46 people asking questions in a Zoom thing before. So just unmute yourself and ask questions at any point.
I have a question. So you said that you only looked at the, it was the blue and the purple. You only looked at those two things because you didn't have time to do the rest of them, are you planning to go through and look? Yeah, right there. Are you planning to go through and figure out the rest of these things?
Not that I have a project that I'm like playing around with some of these ideas, but yeah, like I would like to explore a little bit more from these different ideas, but at the same time, it depends on if I have time after my PhD and stuff like that, because I still need to finish some stuff. So it might just take a while, but I'm actually very interested in exploring them.
I'm also going to announcement. There's a text chat. You can ask questions there. And I promise to stop the recording. So I'm going to do that now for the question session.